So we were working on a problem using dynamic programming approach for generating an optimal binary search tree. So in continuation with the previous session, in the previous session, we have started working on the given optimal binary search tree problem. And we have generated this table as the first step. So in any dynamic programming method for solving any given problem, there will be two steps. So the first step is where the given problem will be divided into sub problems, and we'll try to solve the sub problems for one time, for once, and then the solutions for all the sub problems will be tabulated. So we did the same when we solved 0-1 knapsack problem. We have generated sets information and stored it in a table. So traveling salesperson problem also, we did it in the same way. Here optimal binary search tree also, it's the same situation where we are going to divide the bigger problem into sub problems. We'll solve the sub problems. We'll try to tabulate all the solutions for the sub problems. We'll try to store it. So this is the table where the given binary search tree problem is divided into many sub problems. You can see here I have divided the given bigger problem into sub problems. C of 0, 0 is a sub problem. C of 1, 1, C of 1, 2, C of 2, 3, all these are sub problems. So I have divided a bigger problem into sub problems. I have also tried to solve the sub problems and tabulated the results, tabulated the solutions. Once solutions to all the sub problems are ready, then from this tabulated information, we are going to extract the final result for the given problem. So once I have tabulated this for any given problem, I have prepared a table. So I will start preparing the optimal binary search tree. I will start constructing the optimal binary search tree by taking the information from this table. So I'll start. So I have to first start by deciding which key will act as the root. So in the given problem, there are 3 keys that are given, and the keys were 10, 20, and 30. So there were 3 keys. We have to build a binary search tree to store these 3 keys. Now, among these 3 keys, which key will act as the root? Which keys will go into the left subtree? Which keys will go into the right subtree? And so on, we have to decide. Okay, so for deciding that, I'll start from the bottommost table, bottommost row in the table. I'll start here, the bottommost row in the table, and I'll check which key will act as the root of the BST. So I can see here R03, that is root of the BST with nodes 0 to 3. The optimal root for this tree, it is decided to be key number 2. So that is, this is 2. Second key is 20. So it has been decided that 20 is optimal key to act as the root of the tree. So we'll start extracting the information from the table. First, I'll check that R of 0, 3 equal to 2. That means second key will act as the root of the tree. So I'll start writing. I have taken this information from the table. R root of the tree with nodes 0 to 3 is 2. So second key will act as the root. So I have drawn here the root of the binary search tree. And which key will act as the root of the binary search tree? Key number 2. Key number 2. Now, given k is equal to 2, applying the formula of the dynamic programming, now r0, 3, I'm going to divide it into left child, right child, sorry, left subtree, right subtree. So among all these keys, r of 0, 3, there are these many number of nodes in the BST. Among all this, second key will act as root. The remaining keys, some of them should get into left subtree, some of them will get into right subtree. Now, which keys will go left side, which keys will go right side? All the keys which are greater than, which are less than k. All the keys which are less than k will get into the left subtree. All the keys which are greater than k should be kept in right subtree. This is the rule for the binary search tree. Given a parent, all the values less than parent will get onto the left subtree. All the values greater than parent will get into the right subtree. Now, according to this, our k value now is equal to 2. What are all the k values that are less than 2? For that, I'm going to write the root of 0, 1. How did I write this? The formula that I have used. If I have to write C of I, j, how did I write it? I wrote it C of I, k minus 1 will form the left subtree. C of k, j will be your right subtree. This was the formula that we have used. This recursive formula represents the dynamic programming approach. So if I is 0, j is 3, C of I, k minus 1. K is here 2. K is equal to 2. So this will become, left subtree will become I, k minus 1. So it is R of 0, 1. What will be the right subtree? Right subtree will contain k, j. K, j is 3. So it is R of 0, 1. Left side, R of 2, 3 will be on to the right side. So using the formula I, k minus 1. K, j. So using this formula, I have split the remaining keys into two parts, left subtree and right subtree. So I have written this. I have written R03. I have divided into I, k minus 1 to the left, k, j to the right. Now, what is R of 0, 1? Check the table. R of 0, 1 is 1. R of 2, 3, the value is 3. R of 2, 3, the value is 3. That is, once the root of the tree is decided, the next step is to decide out of the remaining keys, which key should act as the root of the left subtree. So here on the left side, you'll have left subtree. Left subtree will again have a root. Again, it will have left and right. So this is a recursive process. So once root of the tree is decided, you have to then decide who will act as the root of the left subtree, who will act as the root of the right subtree. So now by using these values, it is decided. The root of the left subtree will be key number 1. The root of the right subtree will be key number 3. These are the key numbers. 2, 1, 3, these are the key numbers, right? So First key, k equal to 1, first key will act as the root of the left subtree. K equal to 3, that is third key, will act as the root of the right subtree. So once I have k equal to 1, k equal to 3, these are the roots of the subtrees. Now again I have to repeat this process. It's a recursive process. So I'm going to again divide left and right. Now this is the root. Now you have left subtree and right subtree. Now here, which of the remaining keys will get into left side? Which of the remaining keys will get into right side? For that, you check this. R of I, comma, j. K is equal to 1. So here the values are I equal to 0, j equal to 1, and k equal to 1. Now you have your I, j, k values. Write down the formula. This is left side will be R of I, comma, k minus 1. Right side, you are going to write it as R of k, comma, j. You have written left and right, you have written. Okay, so for this also you are going to write I value here is 2. This is I, this is j. So I is 2, j is 3, k is 3. It will have left, it will have right. What will be the left side? R of I, comma, k minus 1. What will be the right side? R of k, comma, j. Now, whenever you have your I is equal to j, you'll stop there. Your tree stops there. So you can see R of 0, comma, 0. The tree construction stops. That branch stops there. That branch stops there. R of 1, comma, 1. So this branch stops here. R of 2, comma, 2. This branch also stops construction here. R of 3, comma, 3. This also stops here. So what is, you have got like this. So your construction of the binary search tree stopped here. So you had 3 keys. So within the optimal binary search tree, there are 3 keys, and you have decided which key will act as the tree root, which will get into left subtree, which will get into right subtree. You have decided. Once this is ready, with the k values, check this table and construct your optimal BST. Because here we have written k equal to 2, k equal to 1, and so on. These are key numbers. 1, 2, 3 are key numbers. So here I have given numbers to the key 1, 2, 3. So according to this table, I'm going to replace key number 2. Key number 2 is 20. So I'll write 20 here. Key number 1, key number 3. 10 and 30. So this is your final optimal BST that you have constructed using dynamic programming. Now, this is the optimal BST. Now, what is the cost of this optimal BST? Cost of the optimal BST represents the cost of the average cost of the search operations. This cost of the tree represents the average cost of the search operation. Now, what is that? That is nothing but equal to cost of 0, 3. What is cost of 0, 3? You can see the table. Cost of 0, 3. You can see this table. 27. So here it is 27 divided by 14. Why I'm dividing by 14? Because as I said, when starting working out this problem, actually the information was these will be probabilities. P of I represents probabilities of a successful search. Probability of a successful search. Q of I represents the probabilities of unsuccessful searches. Probabilities will be in the values 0 to 1. So the given values were 2 by 14, 1 by 14, 4 by 14, and so on. These were the values given. But for simplicity of the mathematical calculations, I have not used the denominator divided by 14. I did not use while forming this table and performing multiplications, additions. I considered only numerators. 2, 1, 4 I considered. I did not consider divided by 14. No, you consider them. You have to actually consider it. So what I did is, finally, I am saying that this is the cost. 27 is the cost. Actually, 27 is not the cost. By 27 divided by 14 is the actual cost of the binary search. So this is how, given a BST problem, you are going to use dynamic programming approach and generate an optimal BST and also calculate the cost of the optimal BST. This is dynamic programming algorithm for generating the optimal BST. There are two procedures, two methods. The first method is called as OBST algorithm, and the second algorithm is find algorithm. So you have two algorithms which form the dynamic programming algorithm for optimal BST. Now, what is this algorithm OBST? This is going to generate the table, the bigger table that we have calculated. That table will be generated by this algorithm. And it takes parameters P, Q, N, where P is the array representing the probabilities of successful searches. Q is the array representing unsuccessful searches. N is the number of keys given. These three input parameters will be received, and this algorithm generates an output, which is the table. It's an array again. It's a table. It is going to give you a table consisting of all the costs and the optimal routes at each step. C of I, j, R of I, j, and W of I, j, weights, costs, and optimal routes. These three values will be tabulated, and the two-dimensional table will be the output of this algorithm. So this is a for loop here for initializing the values in the table. So how did we start calculating the table? How did we form this table? If you remember the procedure, whenever I value, j value equal to 0, the 0th row, how did you fill it up? W of 0, 0 is Q of 0, 0. W of 1, 1 is Q of 1. This is how we have initialized the weights. Then what did we do? C of 0, 0 and R of 0, 0. We have taken all zeros. Right? So this is the thing. Whenever I and j are equal, it is I, I, and the weight of I, I will be equal to Q of I. And the cost and root of I, I will be initialized to zeros. This is 0th row. Once this is initialized, I have to fill up the remaining weights, right? So how did we fill up the remaining weights? Remaining weights, weight of 0, 1 will be equal to weight of 0, 0 plus P of j, Q of j. That was the formula. The formula was weight of I, j is equal to weight of I, j minus 1 plus P of j plus Q of j. So this is the formula that is written here. W of I, j is equal to weight of I, j minus 1 plus P of P of j and Q of j. So this formula will give you the weights. Roots and then further costs will be initialized. Then this is the loop where all the remaining costs and the remaining weights will be initialized. Okay, so there is a nested loop. You are going to calculate the costs. You are going to calculate the roots. It's the general formula, the recursive formula that we took. C of ij is equal to C of I k minus 1 plus C of kj plus weight of ij. But we have to take here minimum values, and for taking minimum values, I'm using the find algorithm. So you'll have many possible values for k. So which one is minimum? I have to find it. So for that finding, I have this find algorithm, find procedure. This is tabulation. Write operation is where the results, cost, weight, and root values will be written into a table. Now, this is find algorithm for finding out, given a I value, j value, and k value, which is the minimum cost function, the minimum value that we are going to find out. Right? So the time complexity of this dynamic programming algorithm for OBST is big O of n square if you are using notes result to limit for checking the values of k. So this find algorithm will take different values of k and check for the minimum cost function. So in general, what I'll try to do is I'll check the cost functions for all possible k values. It will take more time. Actually, it will take n cube time. If you are going with blind force approach and finding the cost functions for all the possible values of k, then the time complexity will be n cube. Otherwise, if you are using notes result to limit to which k values you want to check, you'll not check the cost function for all the values of k. You'll select. Now that selection for which values you'll find the cost function, that depends upon some technique which is called as notes result limit. If you're using that, then the time complexity is reduced to n square. This was the session on optimal binary search tree problem using dynamic program. So in the previous session and in this session, I have discussed what is a binary search tree, what is an optimal binary search tree, how to find the cost of a BST, what is dynamic programming formulae for solving this problem. I have also worked out a problem and I have also presented the algorithm and the time complexity for this set.